Okay, this video lesson is on power and energy in circuits. So let's start off with the definition of power. This is a definition that we met in mechanics. Power is the rate at which energy is transformed. So in mechanics we talked about the power that a weightlifter might use when they're lifting weights, and that would be the rate at which they're transforming their chemical energy and doing mechanical work with it and lifting something. What we're going to do in this video is talk about how power can be expressed in electrical terms and look at how it applies to circuits. So I'm going to start off with just a formula version of that definition, which states that power is equal to U over T. So U is going to be our expression for energy. Okay. And we're dividing by T because we have a rate. And what we want to do right away is we want to get this kind of general formula in terms of electrical quantities. So let's think about a circuit and what does it mean for energy to be transformed in a circuit. And what it means is that basically you're going to be moving a certain amount of charge through a certain potential difference. So I'm going to replace the potential energy term there with Q times V, because that product of charge times a voltage difference is actually another way of expressing the energy difference, the energy transformation in a circuit. By the way, when I write V, it implies it's a voltage difference here. I'm not going to use the delta symbol when I talk about this. So V is just implied as a voltage difference. Okay. So now we have a definition of power that's in electrical quantities. Unfortunately, it's kind of difficult to measure charge in circuits directly. So it's much easier to look at this quotient which shows up, which is charge over time, and that's just the definition of current. So this leads us to a nice formula for power, which states that power is equal to current times voltage, and that's actually called Watt's law. And it's in terms of electrical quantities which are very easy to measure. It's easy to measure current with a meter. It's easy to measure a voltage difference with a meter. And current contains kind of the rate information, and the voltage difference is kind of static, but that's where the energy is coming from. So this has kind of got everything pulled into it in terms of electrical quantities. From a units point of view, power is measured in units of watts. And the units work out here so that 1 watt of power is equal to 1 amp times 1 volt. And so that's nice and simple. This formula is useful. It's used by electricians and people in the home very often. If you want to figure out how much power an appliance uses, all you have to do is multiply the amps times the volts. So maybe you've got like a power tool that uses, say, 2 amps of current, and it runs at a voltage of 110 volts, kind of your standard outlet. So the power that particular tool would be using would be 2 times 110 or 220 watts. And that's a really easy formula to use. So that 220 watts tells you the rate at which electrical energy is being converted into other forms in your drill or your saw or whatever it is. Okay, so that's what that means. Now, in a lot of things that we're going to talk about in class, we're going to talk about resistors as being devices which dissipate heat. So a resistor is basically something which is generally designed to dissipate heat. And so sometimes it's more useful to express Watt's law in a couple of different ways where we talk about the resistance explicitly. And the way that you can get those other forms is to substitute using Ohm's law. So I could substitute for current and instead write voltage divided by resistance and multiply that times voltage. Okay, so substituting here and here. And this gives me one other version of Watt's law where power is equal to voltage squared divided by resistance. Another way which is very commonly used, probably more commonly used, is to replace the voltage part from the original formula with I times R, again from Ohm's law, and this gives the formula that power is equal to current squared times resistance. This formula is probably used more, and a lot of times this is called the resistive heating formula, because it kind of makes the point that the power that's used in a resistor is going to be directly proportional to the square of the current going through the resistor. So as the current increases, the power that gets used in the resistor goes up fast, goes up as the square. This can be a bad thing. For example, if you have power lines, you want to keep the current as low as possible so that you're not wasting a lot of power heating up those lines. Okay, so maybe we'll do that example at the end of this lesson. So oftentimes you want to reduce the current to keep the power down. Okay, so let's take a look at how we can use Watt's law and apply it to a circuit that has a battery with internal resistance. So I'm going to draw that circuit right here, and remember that a real battery consists of an EMF, but you also have to subtract a small voltage difference because of the internal resistance of that battery. Okay, so this whole thing is my battery, and then in the external circuit, I'm going to place the load. That's going to be uppercase R, and that's the thing I actually want to provide the power to. So this could be my drill, it could be a microwave oven, it could be a flashlight bulb. Okay, so now let's take the Watt's law formula and look at the power that we can get out of this battery. And the way we do it is to apply Watt's law and to say that power is equal to current times voltage, except now we're going to recognize that the voltage that we get out is actually the terminal voltage, not the EMF. So that terminal voltage is going to be reduced by this internal resistance. So let's carry this out. Terminal voltage is going to be given by the EMF minus current times internal resistance. And then you can see that power that I get out is actually going to be equal to kind of an ideal power, which is going to be current times EMF minus kind of a heating term here. Okay, so I squared R is literally the power that's basically used up heating the battery as charge pushes its way through the battery. It's very much about the inefficiency of the battery. Okay, so this is actually not a good thing because it's reducing our output power. So, for example, what if we have an EMF of 12 volts? Let's assume a perfect world where the internal resistance is 0. And let's say that we want to operate a 6 ohm light bulb filament. So the power that I could get ideally is going to be equal to my current, which will be 12 volts over 6 ohms, times my EMF of 12 volts, minus I squared times R, but there is no internal resistance, so there's nothing to subtract. So my current here is going to be 12 divided by 6, that's 2 amps. 2 amps times 12 volts is 24 watts. So that's kind of the most power that I could get out of this battery. Okay, what if my internal resistance was equal to 1/2 of an ohm? So I hope that you would kind of predict that you're going to get less power. And the question is how much less do we get? So now the power out, we have to refigure this. It's going to be 12 volts, but to find the current, I now have to divide by not 6 ohms, but 6.5 ohms, because I have to add this into the circuit. Remember, these two resistors are in series with each other, so the total resistance is 6.5 ohms. I multiply this by 12 volts again, okay, and then I have to subtract I squared times R. So again, I'm going to have 12 over 6.5 squared times 1/2 of an ohm. And approximately what this is going to give me is I'm going to get about only 22 watts from this first term. Notice that's less than what we had before. So from the get-go, we actually have less watts to begin with. And I've got to subtract, I think it's about 1.7 watts that comes from here. And so that's really kind of knocking this down. That knocks this down to what, about 20.3 watts. So the overall effect of having internal resistance, even of just 1/2 of an ohm, really reduces my power from 24 watts down to about 20 watts. And so that's kind of the effect that this can have if you have a battery with an internal resistance. Okay, and let's just look at one other example here. This is kind of a more practical example of how power gets to your home. I don't know if you live in a home that looks like that, but let's say that you do. And let's say that you have an appliance that needs 1,000 watts of power. Okay, so maybe this is a space heater in your house. Now, that space heater is probably plugging into a 100-volt circuit or something close to it. So the current that you will be needing in the space heater is going to be given from Watt's law. It's going to be power over voltage. It will be 1,000 watts over 100 volts. It's going to be 10 amps, which is a lot of current, but maybe this is something like a space heater. Okay. So, fine. The question here, though, is like, what's the smartest way to get that power to your house from the power company's point of view? Because there's a smart way and there's a not so smart way. So let's look at both ways. I'm going to draw power lines here. This is going to be my power station. And, you know, power lines can be many miles long. They're usually made from pretty good conductors, but when a conductor is long enough, you know, remember the resistance is going to grow. So let's say that these power lines have a resistance of about 50 ohms. Okay, that's actually not unreasonable for cables which could be several miles long. So the question would be, like, what does the power station have to actually get to you? So let's go the first route, and let's say that the power company is going to try to get you your 1,000 watts by directly giving you 10 amps of current. Okay, so that you're sending these 10 amps so that when it gets to your house at 100 volts, you can do your thing. Okay. Well, there's a couple things you're going to lose big time when this happens. Number one, the first thing you're going to lose is voltage. So you're going to lose voltage just in the power lines themselves. Okay. Just getting those amps to your house. How much are you going to lose? You're going to lose Ohm's law. Okay. In other words, the voltage you're going to use, the voltage drop in the lines is going to be I times R, 10 amps times 50 ohms. Oh my gosh, that's 500 volts. So the very first thing that might surprise you is that in order to deliver this 10 amps to you, the power company is going to be losing 500 volts to send them to you. So can you see, in order to get you your 100 volts, if you're losing 500, the station has to send or create a potential difference of 600 volts. Okay. Now there's another problem which is maybe even almost bigger, and that is what power do you lose here? And the power that you lose is going to be equal to I squared times R. And this is going to be impressive because you're going to have a current of 10 amps squared times a resistance of 50 ohms. That's going to be 100 times 50. That's going to be 5,000 watts of power. And so, in order to give you your 1,000 watts, the power company needs to actually put out 6,000 watts because 5,000 of them are going to be lost heating up this wire. Those are my little symbols for heat rays. Okay, and so that's a problem. This is very expensive, not good. Okay, so let's think of a better way. A better way would be if you could actually send less current. What if we could basically do the job here by sending less current, maybe a current of only 0.1 amps instead of 10 amps? You can see right away that my voltage drop in this case would only be 5 volts, and power that I lose is going to be 0.1 squared times 50, which I believe is only 1/2 of a watt. So that's like a lot less power loss, and it's a lot less voltage loss that's going on there. Okay, that'd be much better. So the way to do that is to say, well, okay, in this case, if I'm only losing 1/2 of a watt, but I'm using 1,000 in my home, well, basically the power station is pretty much giving me a power that's about equal to 1,000 watts, right? It's 1,000 plus 1/2, but I'm not even going to worry about that. And I want to get that through the wire somehow. So I can think about Watt's law. Watt's law says that power is equal to current times voltage. So I want my 1,000 watts to get there, but I only want to use a current of 0.1 amps, right, to get it there. So this is my Watt's law. So the question is what voltage, needs to be generated at the station, and the voltage that you need here is actually very large, right? Because if you cross divide by 0.1, this becomes 10,000, and the voltage that the power station is actually going to be generating is a very high voltage of about 10,000 volts, or at least it's going to transmit the power. Now that might seem like a bad thing, but it's not, because the way that this works is that you have a transformer outside the station which will transform the voltage up to 10,000 volts so that you can carry a very low current through the wires. Now, someplace in your neighborhood, you're going to have a transformer, maybe behind your house, and that transformer is going to step that voltage down. Okay, you're only losing 5 volts, by the way. So when the volts get to your house, you're going to be getting something like 9,995 volts. Okay, so you're not losing many volts in between the station and your transformer, but you do need to step them down, and the transformer is a very efficient device, and that will step it back down to 100 volts. So this is way, way more efficient, because now if you look at this, the power station itself is only basically generating 1,000 watts of power to give you your 1,000 watts. Okay, you're losing very little power in the lines. Only about 1/2 of a watt goes into heating, and the current that's flowing through the wires is much, much lower than what it was before. The thing you have to do to make this work is you have to have transformers. You have to have things which can step the voltage up to very high voltages through the lines. But like I said, the technology for that is quite efficient, and it's not that expensive. So this is why power lines are basically operated at a high voltage, so that you have very little resistive heating loss. So I thought that would be a nice example to end with on Watt's law, kind of a practical component to it. Okay, so hopefully in the lesson we've learned a little bit about the different forms of Watt's law, how it applies to a battery with an internal resistance, and a practical example of how power gets to your home.